Something is coming. It has no star. It produces no light. It emits no signal that any radio telescope on Earth has ever detected. It moves through the galaxy in absolute darkness, at tens of kilometers per second, following a trajectory that has been set since the moment it was ejected from its birth system. A trajectory that, in the current epoch of the universe's long history, happens to be aimed at us. Not metaphorically aimed, not approximately aimed at the solar system in the precise technical sense that its gravitational interaction with the Sun will bring it through the planetary region, through the orbits of the worlds you know, through the space where Earth moves around the Sun at 30 kilometers per second, completely unaware. You cannot see it coming. No current telescope can. And by the time any instrument on Earth detects it, the question will not be whether it changes the solar system. The question will be, how much? If you enjoy videos that take the universe's most extreme scenarios and follow them to their honest physical conclusions, no comfort, no softening, just the science, I'd genuinely appreciate it if you hit that like button and subscribe. It helps more than you know. Now, settle in, get yourself nice and comfortable. Let's begin. The first thing you need to understand is that this is not a hypothetical invented for the sake of drama. Rogue planets, planets that travel through interstellar space unbound to any star, dark and cold and invisible, moving alone through the galaxy, are not theoretical constructs. They are real. They are extraordinarily numerous. Current estimates, based on gravitational microlensing surveys and statistical modelling, suggest that there are more rogue planets in the Milky Way than there are stars. The galaxy contains somewhere between 100 and 400 billion stars. There may be 1 trillion rogue planets. There may be more. Planets the size of Earth, planets the size of Jupiter, planets larger than any world in our solar system, all of them dark, all of them cold, all of them moving through the interstellar medium in complete isolation, following trajectories that cross and recross the galaxy over billions of years. The galaxy is not mostly stars and gas and dust. It is mostly things we cannot see. And among those invisible things, in numbers that dwarf the stellar population, are wandering worlds. How did they get there? This is where the story begins, not with the arrival, but with the ejection. Because understanding how rogue planets are born tells you everything about what they are and what they carry with them when they travel. In the early history of a planetary system, in the first 1,000,000 to 100 million years after a star forms, when the protoplanetary disk of gas and dust around the young star is condensing into solid bodies, the process of planet formation is extraordinarily violent. The standard model of planet formation, called core accretion, describes a process in which small particles of ice and rock stick together through electrostatic forces, building up from dust grains to pebbles to planetesimals, rocky bodies a kilometre or more across, to planetary embryos. These embryos then collide and merge in a phase called the giant impact phase, in which the inner solar system is a shooting gallery of large bodies smashing into each other at kilometres per second, building the terrestrial planets through a sequence of catastrophic mergers. The Moon was formed in exactly this way. A planetary embryo, roughly the size of Mars, struck the proto-Earth at an angle, and the debris of that collision, flung into orbit, coalesced into the Moon over the following centuries. Every world in the solar system carries the scars of this violent early history. But here is what the models consistently show, across dozens of different simulations of planetary system formation, using different initial conditions and different physical assumptions. Most systems form more planets than they keep, The gravitational interactions between forming planets are chaotic, and in chaotic systems, the long-term outcome is determined by the accumulation of tiny perturbations that amplify over time. A planet that forms in the right place, or the wrong place depending on your perspective, gets a series of gravitational nudges from its neighbours, each nudge small, each nudge adding to the last, until the cumulative effect is a change in its orbit so large that it crosses the orbit of another planet. Crossing orbits mean close encounters. Close encounters mean more extreme gravitational perturbations. And eventually, in a sequence of interactions, the model shows not merely possible, but common, in some simulations, nearly inevitable. One of the planets is ejected entirely. Not perturbed into a different orbit, not pushed to the outer system. Ejected, given enough velocity to escape the gravitational well of the star completely and enter interstellar space. This happened in our own solar system. There is strong evidence embedded in the orbital architecture of the giant planets and in the structure of the Kuiper Belt and Oort cloud that the early solar system contained more planets than it does now. The NICE model, a theoretical framework developed by a group of planetary scientists in Nice, France, in the mid-2000s, proposes that a solar system once contained a fifth giant planet, a world comparable to Uranus or Neptune in mass, which was ejected into interstellar space approximately 4 billion years ago during the late heavy bombardment, the period when the orbits of Jupiter and Saturn crossed a 2-1 orbital resonance and drove the other giant planets into a phase of chaotic migration. The ejected planet, if it existed, is somewhere in the galaxy now, a rogue world the size of Neptune, dark and frozen and alone, carrying the chemical fingerprint of our solar system's outer disk, moving through the interstellar medium in complete isolation, unidentifiable among the trillion others like it. We sent one of our own into the dark. This is how common ejection is. The galactic population of rogue planets is dominated by lower mass objects, Earth mass and sub-Earth mass worlds, because lower mass planets are more easily perturbed into ejection by their more massive siblings. But the population includes everything from Mars-sized bodies to super Jupiters, planets 10 or 15 times the mass of Jupiter, so large they'd blur the boundary between planet and brown dwarf star. The largest rogue planets retain significant internal heat from their formation, warming their interiors for billions of years through radioactive decay, and some may maintain liquid water oceans beneath thick hydrogen atmospheres, heated by geothermal energy alone. These are the most exotic objects, planets that may have conditions conducive to chemistry, to complexity, perhaps to something more, despite having no star, heated entirely from within. Drifting through the dark, with their oceans sealed beneath hundreds of kilometers of hydrogen-rich atmosphere and ice. But the one that is coming toward us, the one at the center of this thought experiment, is not one of those. It does not have a liquid ocean. It is not warm. It is a world approximately the mass of Jupiter, 300 times the mass of Earth, 1.9 times 10 squared 7 kilograms, and it has been alone in the interstellar medium for approximately 2 billion years. Its surface temperature is around 30 degrees Kelvin, 30 degrees above absolute zero, cold enough that nitrogen freezes solid on its surface, cold enough that the atmosphere, whatever remains of it, has largely frozen out onto the ground over the billions of years since ejection. It moves through the interstellar medium at approximately 26 kilometers per second relative to the local standard of rest, roughly the average velocity of stars in the galactic disk, and its trajectory, set by the gravitational dynamics of its birth system and subsequent encounters with passing stars over 2 billion years, is bringing it toward the sun. To stand on this world, an act of imagination only, since no physics permits it, would be to experience something that no science fiction author has ever fully captured. Because the ingredients of the experience have no earthly parallel, and the human mind has no template to process them. The gravity at the surface would be approximately 2.5 times Earth's gravity. Every kilogram of your body pressing down with 2.5 times its normal weight. A crushing heaviness that would make walking difficult and long-term survival impossible without mechanical assistance. The sky above would be black, not the blue-black of an airless moon, but the dense black of a world that has been separated from its star for 2 billion years. A world around which no sun rises. A world whose sky has never been lit by anything except the distant, faint glow of the Milky Way. There are no seasons, there is no day-night cycle. There is only the permanent darkness, the permanent cold, the slow tick of radioactive decay in the interior, providing a microscopic trickle of warmth that is entirely insufficient to make the surface anything other than what it is. The coldest place a world can be, while still being a world. The surface itself is a strange and alien landscape. What was once, 2 billion years ago, the cloud tops of a gas giant, a world of swirling hydrogen and helium storms, of banded atmospheric circulation like Jupiter's, of lightning storms as large as continents, and storm systems that persisted for thousands of years, has frozen. The upper atmosphere, as the temperature dropped in the centuries after ejection, began to precipitate. First, the heaviest volatiles, methane, which freezes at 90 Kelvin, began to snow out of the atmosphere at temperatures the upper cloud deck reached within few decades of ejection. Then hydrogen sulfide at 82 Kelvin, then argon at 87 Kelvin, then nitrogen at 63 Kelvin. Each compound snowed out in sequence as the atmosphere cooled, leaving a world whose surface is layered in frozen volatiles in the order of their freezing points, a geological stratigraphy not of rock and sediment, but of frozen gas, accumulated in layers over 2 billion years, each layer representing a different era of the atmosphere's slow death. The deepest layers, beneath hundreds of meters of frozen volatiles, are where the original cloud-top aerosols are preserved, the organic haze compounds, the phosphine and silane and ammonia that characterize the upper atmosphere of the gas giant in its birth system. These compounds have been frozen in place for 2 billion years, perfectly preserved at 30 Kelvin, a chemical fossil record of a solar system that no longer exists in the form it had when this world was ejected. If you could drill down through the frozen nitrogen and methane and argon, through the organic haze layers, deep into the interior where the temperature rises due to radioactive decay, you would find, at some depth, a layer of liquid, probably liquid hydrogen, under the enormous pressure of the overlying material, behaving like a metal rather than a gas, the metallic hydrogen layer that gives Jupiter its extraordinary magnetic field. Below that, at the very core, a rocky and icy center that has retained heat from formation even after 2 billion years, a small, warm heart in an otherwise frozen world. Crossing this world's surface, you would move across a plain of frozen nitrogen, so perfectly flat that the horizon at the scale imposed by the world's large radius, is further than any terrestrial horizon. A vast emptiness interrupted by the occasional ridge of accumulated frozen material from some internal process that shifted the surface over geological time. The Milky Way overhead, and it is overhead everywhere, in all its 2-billion-year-old glory. A band of light that has been this world's only consistent illumination since it left its star, casts a light so faint it is less than the light of a quarter moon on Earth. You would need dark adapted eyes to see by it, and what you would see in that dim galactic light is a world that has never been named, never been visited, never been mapped. A world that formed in a solar system that no longer exists and has been travelling alone through the galaxy for longer than complex multicellular life has existed on Earth. This is what is coming. Not a rock, not a comet, a world. A world with its own internal geology, its own frozen chemical history, its own strange and alien surface, moving through the space between the stars at nearly 100,000 kilometers per hour, indifferent to everything in its path. Following the trajectory that gravity set for it 2 billion years ago, and that nothing in the solar system can alter by a single kilometer. It is, right now, approximately 2 light years away. That is close. Proxima Centauri, our nearest stellar neighbour, is 4.24 light years away. This rogue planet is closer to us than half the distance to the nearest star, and it is moving toward us at 26 kilometers per second. 26 kilometers per second, roughly 93,000 kilometers per hour. At that velocity, it will cross the remaining 2 light years, approximately 18.9 trillion kilometers, in approximately 23,000 years. Not an instant, not a geological epoch. A time frame that human civilization has already spanned. Göbekli Tepe, the oldest known megalithic structure, was built approximately 12,000 years ago. Writing was invented approximately 5,000 years ago. The rogue planet will arrive in twice the time, separating us from the first cities of Mesopotamia. It is coming. The only question is what happens when it gets here. The answer depends on something that seems almost insultingly simple, given the scale of the event. Where exactly does it go? The trajectory of the incoming world, combined with the gravitational influence of the Sun and the planets, determines everything. There are 3 broad categories of outcome, ranging from disruptive to catastrophic to extinction level, and the difference between them is a matter of geometry, a matter of how close the rogue planet passes to the Sun at its closest approach, a number called the perihelion distance. If the perihelion is beyond Jupiter's orbit, beyond 5 astronomical units from the Sun, where 1 astronomical unit is the distance from the Earth to the Sun, approximately 150 million kilometers, the encounter is gravitationally significant but survivable for the inner solar system. The rogue planet swings around the Sun, perturbing the orbits of the outer planets, potentially dramatically reshaping the Kuiper Belt and Oort cloud, and exits the solar system on a hyperbolic trajectory, never to return. The inner planets, Mercury, Venus, Earth, Mars, survive. Their orbits are perturbed. Some perturbation may be large enough to matter for life over millions of years. But the event itself, while unprecedented in the history of recorded civilization, does not end the world. If the perihelion is within the inner solar system, within 2 or 3 astronomical units, approaching Earth's orbital distance, the gravitational dynamics become catastrophic. A Jupiter-mass body at 2 astronomical units from the Sun exerts gravitational forces on the inner planets that are comparable to and in some configurations exceed, the gravitational forces the Sun itself exerts on those planets. The orbits of the inner planets destabilize. Some may be ejected from the solar system. Some may collide. Earth, caught between the gravitational influence of the Sun and a Jupiter mass intruder at close range, may find its orbit changed beyond any possibility of recovery. Not in the geological sense, in the orbital mechanical sense, on a timescale of years to decades. And if the perihelion is very close, within the orbit of Mercury, within half an astronomical unit, the situation escalates into a regime that defies easy description. Tidal forces from the rogue planet would disrupt bodies in the inner solar system. The gravitational dynamics will be so chaotic that predicting individual outcomes with precision becomes computationally intractable. The statistical outcome is clear. The inner solar system, as we know it, ceases to exist as a stable configuration. But we are getting ahead of ourselves. Let us begin where the story actually begins, not at the moment of closest approach, but at the moment of first detection. Because the story of a rogue planet encounter is not just the story of what gravity does to orbits, it is the story of what knowledge does to a civilization. You are living your life in some year, approximately 20,000 years from now. If we take the transit time literally, then this thought experiment is equally valid at any detection distance. The first indication that something is wrong comes not from a telescope, but from a model. An astronomer, or whatever the computational descendant of an astronomer is, notices a statistical anomaly in the trajectories of long-period comets. Long-period comets are objects from the Oort cloud, the vast, diffuse shell of icy bodies that surrounds the solar system at distances of 2,000 to 100,000 astronomical units, that have been perturbed into the inner solar system by gravitational nudges from passing stars or giant molecular clouds. They arrive from all directions, their orbits randomly distributed, following the statistical distribution you would expect from a spherically symmetric reservoir. Except this year, this decade, there is a slight excess coming from one direction. Too many comets from one particular region of the sky. A gravitational source is pushing them. Something is out there. The Oort cloud itself deserves a moment of attention here, because it is the first part of the solar system to register the rogue planet's presence, and because most people have no intuitive sense of how vast and strange it is. The Oort cloud is not a disk. It is a sphere, a nearly perfect shell of icy bodies surrounding the solar system at distances between roughly 2,000 and 100,000 astronomical units. 100,000 astronomical units is approximately 1.6 light years, meaning the Oort cloud extends more than a third of the way to Proxima Centauri. It is so distant that sunlight, travelling at 300,000 kilometers per second, takes more than a year to reach its outer edge. The Sun, viewed from the outer Oort cloud, is indistinguishable from any other star. Just one bright point among many, slightly brighter than the rest, but not dramatically so. The gravity of the Sun at this distance is extraordinarily weak. An Oort cloud object feels the Sun's gravity less than 100,000th as strongly as Earth does. It responds instead to the combined tidal force of the entire Milky Way galaxy, a slow, steady pull that gradually distorts the Oort cloud structure over millions of years. The total mass of the Oort cloud is uncertain. It has never been directly observed, only inferred from the orbits of the long-period comets it sends inward. Estimates range from a few Earth masses to several times the mass of Earth, distributed among perhaps 1 trillion individual objects ranging from snowballs a few kilometers across to bodies hundreds of kilometers in diameter. These objects move extraordinarily slowly. At their distance, a body takes millions of years to complete a single orbit of the Sun. Their orbits are nearly circular, nearly isotropic, randomly distributed in every direction, a shell of slowly drifting ice. When the rogue planet, still at roughly 2 light-years, just entering the outer edge of the Oort cloud's gravitational domain, begins to exert its influence, the effect is subtle but cumulative. The closest Oort cloud objects, those at the near edge of the cloud, around 2,000 astronomical units, feel the rogue planet's gravity as a tidal distortion, a slight preferential pull in one direction. Over centuries, this distortion changes the shapes of orbits, gradually increasing eccentricities in the sector of the cloud facing the incoming object. Objects that were on stable circular orbits develop elongated orbits. Some cross into the Sun's gravitational territory, where the Sun's pull dominates and accelerates them inward. These are the comets that arrive first, the early warning, the statistical whisper in the data that something is pushing from a specific direction. The search that follows this anomaly is one of the most consequential scientific investigations in the history of the civilization. Every telescope with the capacity to look in far infrared wavelengths is pointed at the suspect region of sky. The rogue planet, at 2 light-years, emits thermally at around 100 micrometers, wavelengths invisible to the human eye, blocked by Earth's atmosphere. Requiring space-based instruments with large collecting areas and cryogenically cooled detectors to see. It reflects essentially no sunlight, because at 2 light-years the Sun's brightness falls off by the inverse square law to a level so faint that reflection from a planetary surface produces no detectable signal at optical wavelengths. It is not dark in the way that an absence is dark. It is dark in the way that a black object in a black room is dark, physically present, physically substantial, but emitting at wavelengths that require specialized equipment to detect. The instruments find it. They have to. The Oort cloud disturbance is pointing directly at it, and the thermal emission, while faint, is there if you know where to look with the right equipment. The detection is made not by a single brilliant observation, but by a convergence of evidence, the direction of the Oort cloud anomaly, the thermal emission at the correct wavelength for an object at the expected temperature, the proper motion, the slow drift of the object across successive observations, consistent with its velocity through the interstellar medium. 3 lines of evidence, each pointing to the same object, in the same location, moving in the same direction. The detection is confirmed. What follows the detection is not panic, not immediately. What follows is measurement. Careful, systematic, increasingly precise measurement of everything that can be measured. Distance from parallax, velocity from proper motion and Doppler shift of the thermal emission spectral lines, mass from the gravitational perturbations already visible in the Oort cloud trajectories and refined over years and decades by direct astrometric measurement of the rogue planet's gravitational influence on known distant solar system objects. Size, from the thermal emission spectrum, combined with albedo assumptions, and refined by the apparent angular size as the object closes and eventually becomes resolvable as a disk by the most powerful instruments. The mass estimate comes back 1.1 Jupiter masses. The size estimate, slightly larger than Jupiter's current radius, appropriate for a world of this mass that has cooled over 2 billion years but still retains internal heat from formation. The trajectory is computed. The perihelion distance, the closest approach to the Sun, is calculated with progressively increasing precision as more observations accumulate. The initial estimate has a wide uncertainty range. It might pass at 8 astronomical units outside the orbit of Saturn. It might pass at 1.5 astronomical units inside the orbit of Mars. The difference between those two numbers is the difference between a dramatic but survivable encounter and a catastrophic restructuring of the inner solar system. The civilization waits for more data, watches the uncertainty range shrink with each new observation campaign, and begins, simultaneously, because there is no reason to wait, preparing for whichever outcome the trajectory calculation converges upon. This is the moment when the physics of the situation intersects with the psychology of civilization, and the intersection is profoundly uncomfortable. A civilization that knows, with increasing certainty, that a Jupiter-mass world will pass through its solar system within 1,000 years, faces a problem that no prior civilization in any recorded history has ever faced. Planning for a specific known catastrophe on a timescale longer than any political institution, any economic system, any cultural memory has ever sustained coordinated action. 1,000 years, 40 generations, the distance between the Battle of Hastings in 1006 and the present day, the distance between the Norman conquest and smartphones. Every political institution, every economic system, every cultural framework, every language, every nation that existed in 1666 has been transformed beyond recognition in the intervening millennium. How do you maintain a coordinated civilizational response, a sustained program of preparation, adaptation, and infrastructure development across a period during which the civilization itself will change so completely that its future members may not recognize its past members as members of the same civilization? This is not a rhetorical question. It is a practical one, with a practical answer that the civilization must work out through institutions designed explicitly for multi-century continuity, through physical instrument that requires no institutional memory to function. You do not need to know why a bunker was built to live in it. Through culture and scientific transmission, robust enough to carry the knowledge of what is coming across the generations that separate detection from arrival. The civilization has 1,000 years. 1,000 years is, paradoxically, both a very long time and not nearly enough. Not nearly enough to prevent the encounter. I know it may be more than enough to prepare for it if the preparation is sustained and coordinated. And here is where the scenario intersects with something that feels personal, even though 20,000 years is not personal in any ordinary sense. Because the scenario we have been following, a rogue planet detected at 2 light years, moving at 26 kilometers per second, converging on a perihelion inside the inner solar system is not pure fiction. The physics is real. The population of rogue planets is real. The detection challenge is real. The only fictional element is the specific trajectory, the specific timing, the specific object. The class of events we have been describing happens. It has happened. In the 4.5 billion year history of the solar system, the probability that the solar system has experienced multiple encounters with rogue objects of various masses is close to certainty. The current orbital architecture of the solar system, the specific orbits of the planets, the Kirkwood gaps in the asteroid belt, the structure of the Kuiper belt and Oort cloud is, in part, the record of those encounters. We are living in the aftermath of events like this one. We are the product of a solar system that survived them. What we do not know, and what no current technology can tell us, is whether the next encounter is already set. Whether there is, right now, in the interstellar medium, within 2 or 3 light years of the solar system, a dark world on a trajectory that will bring it through the planetary region within the next 100,000 years. Our current surveys cannot detect a Jupiter mass rogue planet at 1 light-year distance. The Vera Rubin Observatory, currently conducting the Legacy Survey of Space and Time, the most comprehensive optical sky survey ever undertaken, is sensitive to rogue planets only within the outer solar system, where reflected sunlight is detectable. At interstellar distances, the thermal emission is the only signal, and current infrared space telescopes lack the sensitivity to detect a cold rogue planet at light-year distances. The next generation of infrared space telescopes, currently in planning stages, may eventually push the detection limit out to a fraction of a light-year for the most massive rogue planets. But a light-year is not 2 light-years. The detection horizon is not the threat horizon. There is a gap, in principle and in practice, between distance at which we can see what is coming and the distance from which what is coming can affect us. This gap is not a reason for despair, it is a reason for investment. Investment in next-generation infrared space telescopes. Investment in gravitational microlensing surveys that can statistically characterize the rogue planet population even when individual objects cannot be resolved. Investment in the computational infrastructure needed to run high-precision solar system dynamic simulations that can rapidly assess the orbital consequences of any detected incoming object. Investment in the planetary defense capabilities that would be needed not to deflect a Jupiter mass rogue planet that is beyond any conceivable technology, but to manage the elevated impact flux from the perturbed asteroid and comet populations that would precede and follow any rogue planet encounter. The threat is real, the preparedness gap is real. The investment needed to close that gap is real, and it is not being made at the scale the threat warrants. But the deepest thing this scenario reveals is not about technology or preparedness. It is about the nature of the solar system itself and about our relationship to it. We live as a civilization, as a species, as a biosphere, in a state of profound dependence on the stability of the solar system. Every agricultural system, every city, every civilization, every species on Earth depends on the sun rising and setting with reliable regularity, on the seasons following their familiar pattern, on the background rate of large impacts being low enough that civilization-ending events are rare on human timescales. We have built everything, every institution, every infrastructure, every cultural tradition, every biological adaptation, on the assumption that the solar system will continue to behave as it has behaved for the entirety of observable human history. That assumption is not physically guaranteed. The solar system is a gravitational system embedded in a galaxy full of dark, massive, moving objects. And it has been stable for 4.5 billion years, not because stability is guaranteed, but because it has been lucky. Lucky in the specific trajectories of the specific stars and rogue objects that have passed near it during those 4.5 billion years. Lucky in the orbital configuration that resulted from the chaotic early history of planetary formation. Lucky in the specific sequence of events that produced a habitable inner solar system with a nearly circular Earth orbit and a large stabilizing moon and a Jupiter shield and an Oort cloud and all the other features that make this system so apparently benign. Luck is not a permanent condition. It is a run of favorable outcomes in a probabilistic process that continues to operate. The process is still running. The galaxy is still full of dark wanderers. The trajectories are still being set by the gravitational dynamics of stellar nurseries and galactic tidal forces, and close stellar encounters that are happening right now in other parts of the Milky Way, producing rogue planets that did not exist a million years ago and will not exist in their current trajectories a million years from now. The universe is not a static backdrop. It is a dynamic system, and the solar system is embedded in it, subject to its dynamics, not immune to its events. The probability of a dangerous rogue planet encounter in any given human lifetime is extraordinarily small, smaller than the probability of being struck by lightning, smaller than the probability of winning a major lottery, smaller than almost any risk that any person takes into account in their daily life. This is a true statement, and it is important, and it should not be distorted in the direction of panic. The solar system is stable, for practical purposes, on any human timescale. You do not need to worry about rogue planets in your lifetime. The probability is too low, but the probability is not zero. Over the 4.5 billion year history of the solar system, over the billions of years of future solar system history that the Sun's remaining lifetime permits, over the full span of time that life on Earth might persist, the probability of at least one dangerous encounter is not negligible. It may have already happened. The early solar system's history includes periods of heavy bombardment that may reflect, in part, the perturbations from close encounters with passing objects. The current configuration of the solar system, the specific orbital arrangement that makes Earth so habitable, is the outcome of a long history that included events we cannot fully reconstruct. We are, in the deepest sense, the lucky survivors of a long and ongoing process. The solar system that produced us and sustains us is not the safest possible solar system. It is the one we got, and it has been good to us, and it continues to be good to us, and most likely, most probably, on any human timescale, it will continue to be. But it is embedded in a galaxy that does not know we are here, does not care that we are here, and does not make exceptions. The dark things moving through the interstellar medium follow the trajectories that gravity sets for them, indifferent to what lies in the way. Most of those trajectories miss us. The ones that do not are not aimed. They are simply going where they are going, and we happen to be in the way. This is the physical reality of our situation. not frightening in the acute sense of immediate threat. Sobering in the deeper sense of a genuine uncertainty about the long-term future, an uncertainty that no technology currently addresses and that most minds never confront. We have built civilization on a platform we did not build and cannot fully secure. The platform is excellent. The platform is stable for all practical purposes. The platform has served life extraordinarily well for 4.5 billion years. But the platform is not invulnerable, and the process that could compromise it is ongoing, operating in the dark, moving at tens of kilometers per second, producing no signal we can currently detect. Something may be coming, we would not know. The dark does not announce itself. It moves, and it waits, and the galaxy turns, and we live on our small warm rock in our carefully balanced orbit, unaware of what is between the stars, as we have always lived, not in danger for now, but never entirely safe. Not entirely safe. Not entirely safe. That is the honest accounting of where we are. We live in a solar system that has been stable long enough to produce us, on a planet that has been habitable long enough to evolve us, under a sky that has been predictable long enough for us to build civilization under it. We have taken all of that stability as a given, as the background condition of existence, rather than the specific lucky outcome it actually is. The rogue planets are out there. The galaxy does not stop turning because we live here. The dark is not empty, and the emptiness is not safe. And the night sky you see when you look up tonight, beautiful and familiar and apparently permanent, is permanent only in the sense that it has been stable in your lifetime and in the lifetimes of everyone you have ever known. On the timescales the universe operates by, nothing is permanent. Everything is contingent. And the contingency is moving right now in the dark between the stars at tens of kilometers per second toward destinations the universe has already decided and has not yet revealed. It looks like the most ambitious engineering program in the history of civilization. It looks like the systematic relocation of populations away from coastal regions that will be affected by the changed tidal dynamics as the encounter approaches. It looks like the hardening of food production systems against climate variability, the development of indoor agriculture, controlled environment food production, agricultural systems that do not depend on specific seasonal patterns that will shift with the changing orbit. It looks like the construction of deep underground habitats, insensitive to surface temperature extremes. It looks like the development of energy systems that are independent of surface, solar flux variations. It looks like the building of a comprehensive planetary defense capability against the elevated asteroid and comet impact threat that will persist for centuries before and after perihelion. It looks like a civilization that has reorganized itself over 1,000 years to be resilient to the specific known threats that the encounter will produce. None of this is comfortable. None of it is quick. None of it is free of sacrifice and political conflict and failures of coordination and periods when the urgency is forgotten because the event is still centuries away and the immediate concerns of daily life overwhelm the long-term planning that the event is conceded to lie. But Jester, situation demands. This is the human dimension of the catastrophe, not the physics, which is precise and calculatable and indifferent, but the civilizational response to the physics, which is messy and political and uncertain in ways that no equation can capture. The mass estimate comes back 1.1 Jupiter masses. The trajectory is computed. The perihelion distance, the closest approach to the Sun, is calculated with progressively increasing precision as more observations accumulate. The initial estimate has a wide uncertainty range. It might pass at 8 astronomical units. It might pass at 1.5 astronomical units. The difference between those two numbers is the difference between a dramatic but survivable encounter and a catastrophic restructuring of the inner solar system. The civilization waits for more data, watches the uncertainty range shrink, and prepares for whichever outcome the trajectory calculation converges upon. Let us follow the worst credible case, not the absolute worst, not a direct impact, but the scenario in which the perihelion is deep in the inner solar system, within 1.5 astronomical units, within the orbit of Mars. Because this is where the physics becomes genuinely extraordinary, and because it is the scenario that reveals what a rogue planet actually does to everything you depend on for existence. Approximately 1,000 years before closest approach, the rogue planet is still at roughly 0.3 light years, about 28,000 astronomical units. At this distance, it has already been influencing the solar system for thousands of years, its gravity gradually nudging the outermost objects of the Oort cloud. The nudges had been sending comets inward in increasing numbers, and the inner solar system has seen a rising tide of cometary impacts over the preceding millennia. Not a dramatic sudden bombardment, a gradual statistical increase. More bright comets in the sky each century, more impacts on the Moon and the outer planets, an elevated flux of interplanetary debris that any monitoring system would have long since detected and characterized. But now, at 28,000 astronomical units, something changes. The rogue planet's gravity is strong enough to begin affecting the Kuiper Belt, the disk of icy bodies that extends from just beyond Neptune's orbit at 30 astronomical units to roughly 50 astronomical units. The Kuiper Belt contains hundreds of thousands of objects, larger than 100 kilometers in diameter, including Pluto and hundreds of similar dwarf planets, and potentially tens of billions of smaller objects. The gravitational influence of the incoming world begins to stir this disk, not catastrophically, not yet, but measurably. Kuiper Belt objects that were on stable orbits begin to show orbital precession, tiny shifts in their orbital parameters that accumulate over centuries. Some are nudged into unstable configurations. Some cross the orbit of Neptune. Neptune, the outermost of the 4 giant planets, with 17 Earth masses, gravitationally scatters many of these new arrivals, sending some inward toward Jupiter, which scatters them further, some ultimately arriving in the inner solar system as short-period comets. The comet bombardment intensifies, not to the level of the late heavy bombardment 4 billion years ago. That was a much more prolonged and extreme event, but to a level significantly above the background rate. An observer on Earth watches the sky fill with bright comets at a rate not seen in the planet's recorded history. Several per year at first, then dozens. Then, as the road planet closes to within a few thousand astronomical units, hundreds. The inner solar system becomes genuinely more dangerous. Not catastrophically so, for a civilization with the technology to track and deflect objects, but measurably and unavoidably more active. At approximately 200 astronomical units, still 20 times further from the Sun than Neptune, the rogue planet begins to have a detectable gravitational effect on Neptune itself. Neptune's orbit is not circular. No planetary orbit is perfectly circular, but it is very nearly so, with an eccentricity of approximately 0.01, meaning it deviates from a perfect circle by about 1%. As the road planet approaches, Neptune's orbital parameters begin to shift. The eccentricity increases. The orbital inclination changes slightly. The changes are small at first, fractions of a percent, but they compound over the years and decades. Neptune is being perturbed. Uranus, Saturn, and Jupiter follow in turn as the rogue planet closes the distance. The outer planets are massive. Jupiter alone contains more than twice the mass of all the other planets combined, but they are not immune to gravitational perturbations. Looks more, they are sensitive to them. In fact, because they are already in a carefully balanced resonant configuration, a product of 4.5 billion years of gravitational evolution that settled them into their current orbital arrangement. The resonances between the outer planets, the near 5.2 resonance between Jupiter and Saturn, the approximate resonances between Saturn, Uranus, and Neptune, are like a tuned instrument. Perturbate one string, and the vibration propagates. The outer planet system, as the rogue planet approaches, begins to vibrate. The vibration matters because the outer planets are the gravitational guardians of the inner solar system. Their massive gravitational fields deflect potential impactors, sweep up debris, and maintain the stability of the inner system. Jupiter, in particular, acts as a gravitational shield, capturing or deflecting objects that might otherwise strike Earth. When Jupiter's orbit is perturbed, its shielding effectiveness changes. The inner solar system becomes more exposed. Asteroidal and cometary material that Jupiter would normally intersect begins to reach the inner planets more frequently. The impact rate on Earth, already elevated by the Oort cloud and Kuiper belt disturbance, rises further. But all of this is prologue. The real drama begins when the rogue planet crosses the orbit of Neptune, entering the realm of the planets proper for the first time. The moment the rogue planet passes Neptune's orbital distance, 30 astronomical units, is not marked by any visible event. There is no flash, no announcement, no sound in the vacuum of space. The Sun, from the rogue planet's perspective, has grown from the point of light it has been for 2 billion years of interstellar travel into a disk, faint but measurable. The brightest object in any sky by far, but still only a small fraction of the brightness it would appear at Earth's distance. The temperature on the rogue planet's surface is marginally higher than it has been. Still well below the boiling point of any known substance. Still deep in the cryogenic regime. But the solar flux is increasing, and materials that have been frozen for 2 billion years are beginning, very slightly, to sublimate. The rogue planet, as it enters the solar system proper, begins to develop a tenuous exosphere, a wisp of vaporized gas surrounding it, too thin to be called an atmosphere, but present. A faint halo of molecular hydrogen and helium, and traces of nitrogen and methane, sublimating from a surface that has been frozen since the age of the dinosaurs. This is the point at which the rogue planet's presence becomes impossible to ignore for any civilization in the solar system. The exosphere is detectable. The perturbed trajectories of Neptune and Uranus are dramatically obvious in any ephemeris calculation. The comet bombardment has been ongoing for centuries, and the trajectory calculation, by now refined to extraordinary precision by thousands of observations over hundreds of years, has converged. The perihelion is locked in at 1.3 astronomical units between Earth's orbit and Mars's orbit, closer to Earth than to Mars. Not Earth crossing, not a direct impact with Earth, but close enough that Earth's orbital stability will be profoundly affected by the encounter. The timeline from here is calculable. The rogue planet crosses Jupiter's orbit 5.2 astronomical units, approximately 40 years before closest approach. The word 40 years sounds like a long time. It is not. Not when what you are timing is the gravitational encounter that will reshape your solar system. 40 years is 2 generations of human political attention. 40 years is the gap between a newly born child and a parent approaching retirement. 40 years is barely enough time in the history of human civilization to go from "this problem exists" to "we have a coordinated global response." In this scenario, the global response has been in preparation for 1,000 years, because the detection happened 1,000 years ago. But even 1,000 years of preparation cannot change the fundamental physics. The rogue planet is coming. The trajectory is fixed. The encounter will happen. The 40 years between Jupiter's orbit crossing and perihelion are the most scientifically productive in the history of civilization, and also, in many ways, the most terrifying. Every observation, every model, every simulation converges on the same answer with increasing precision. The perturbations to the inner planets begin to become measurable within a decade of Jupiter's orbit crossing. Earth's orbital eccentricity, currently 0.17, nearly circular, begins to increase. The change is small at first, a fraction of a percent. But it is measurable, and it is real, and it is the first tangible evidence that Earth's orbit is beginning to respond to the gravitational presence of the approaching world. Mars, being less massive than Earth and further from the Sun, is more sensitive to perturbations. Mars's orbit begins to show measurable changes sooner and faster. The Martian year, currently 687 Earth days, begins to deviate from its expected value. The orbital eccentricity of Mars, already higher than Earth's, increases further. Mars viewed from Earth begins to move across the sky at a slightly different rate than the ephemeris predicts. Not much, not enough to be noticed without precise measurement, but enough to be significant to any civilization tracking these numbers carefully. Venus is also perturbed, and here is where something particularly uncomfortable enters the picture. Venus and Earth are already in a near resonance. Every 8 Earth years, Venus and Earth make very nearly a 13-8 orbital resonance, meaning Earth completes 8 orbits in approximately the same time Venus completes 13. This near resonance is not exact, and over millions of years, gravitational interactions between Venus and Earth are one of the factors that drive the long-term chaotic behavior of Earth's orbit. When an external gravitational perturbation, the rogue planet, begins to change the orbital energies and angular momenta of both Venus and Earth simultaneously, the near resonance begins to be disturbed. The careful dynamical balance that has kept Earth's orbit within a relatively narrow range of eccentricity for millions of years begins to erode. 20 years before perihelion, the rogue planet has crossed the asteroid belt and is now within 3 astronomical units of the Sun, closer than Mars at its furthest extent. It is visible to the naked eye at night, a point of reddish light that has no parallax, that stays fixed relative to the stars, while the stars themselves appear to drift due to Earth's annual orbital motion. Its colour is the thermal emission of its warmed exosphere, a faint reddish glow of reflected sunlight and self-emission combined. Every person on Earth can see it. Every night, it grows slightly brighter. The psychological impact of watching a Jupiter-sized world approach the solar system is not something that any civilization is prepared for by its prior experience, because nothing in prior experience compares to it. The asteroid belt between Mars and Jupiter, the collection of rocky bodies whose total mass is roughly 4% of the Moon's mass, ranging from the dwarf planet Ceres at 940 kilometers diameter down to fragments meters across, begins to be substantially disrupted. The rogue planet's gravity does not pull the asteroid belt apart in one dramatic event. It perturbates individual asteroids through gravitational resonances, the same resonances that normally act as gaps in the asteroid belt, the Kirkwood gaps, where Jupiter's gravity has swept out orbits in 3-1, 5-2, 7-3, and 2-1 resonance with Jupiter's period. With the rogue planet now inside Jupiter's orbit and moving, the resonance structure of the asteroid belt is being actively scrambled. Objects that were on stable orbits are being excited into higher eccentricities. The flux of asteroids crossing Earth's orbit increases by a factor that preliminary models estimate at between 10 and 100 times the background rate. 10 times the normal asteroid flux, 100 times the normal asteroid flux. These numbers need to be calibrated. The background rate of objects large enough to cause regional devastation, objects more than 1 kilometer in diameter striking Earth, is approximately 1 per million years. At 10 times the background rate, it is 1 per 100,000 years. At 100 times, 1 per 10,000 years. These numbers sound manageable over a human lifetime. But the encounter duration, the time during which the rogue planet is close enough to significantly perturb the asteroid belt, is not a human lifetime. It is centuries. The elevated flux persists for centuries before and after the actual perihelion passage. A civilization living through this period faces a dramatically elevated risk of major asteroid impact for a period of hundreds of years. 10 years before perihelion, the rogue planet is now between the asteroid belt and Mars's orbit. It is the brightest object in the night sky, after the Moon, outshining Venus at its brightest by a factor of several. It is visible in daylight, if you know where to look. The gravitational perturbations on Earth's orbit have become measurable without precision instruments. The length of the year is changing. Not by much. Not enough to be noticeable on a day-to-day basis, but by enough that the accumulated deviation over years is measurable in hours. Earth's year is getting slightly longer as the rogue planet's gravity reduces our orbital velocity by a small but cumulative amount. This is not dramatic, it is deeply unsettling. Mars is in worse shape. Mars's orbit has become measurably more elliptical. The red planet's perihelion, its closest approach to the Sun, has moved. Mars is now approaching the Sun slightly more closely than it did a decade ago, and receding from it slightly more. The Martian climate, thin and cold as it is being perturbed by the changing orbital parameters. The Martian polar ice caps, already a delicate balance of CO2 and water ice, regulated by the planet's orbital parameters, are responding. These are small effects. Mars is not habitable in any scenario, and making it slightly less so does not rank as a catastrophe on the scale of what is happening to the inner solar system's dynamics. But it is a measurable change in a planetary climate, driven by the approach of an object not yet within Mars's orbital distance. 1 year before perihelion, the rogue planet crosses Mars's orbit. It is now anterior to the orbit of Mars, moving in a curved trajectory around the Sun, accelerating as it falls deeper into the gravitational well. Its velocity, which was 26 kilometers per second in the interstellar medium, has been accelerated by the Sun's gravity to approximately 45 kilometers per second, faster than any object currently in the inner solar system, faster than Earth's orbital velocity of 30 kilometers per second, faster than anything we have ever built, except the Voyager spacecraft and the Parker Solar Probe at their fastest points. A world of 1.1 Jupiter masses, moving at 45 kilometers per second, passing through the inner solar system at a closest approach of 1.3 astronomical units. The gravitational dynamics in the weeks around perihelion are the crux of everything. This is where the equations of orbital mechanics, combined with the enormous mass of the intruder, produce effects that no prior event in Earth's history has replicated. The tidal force, the differential gravitational pull across Earth's diameter, is not enough to physically deform Earth. Earth is not at risk of tidal disruption. For that to happen, Earth would need to be within a few Earth radio of a Jupiter mass object, essentially touching it. At one point, 3 astronomical units, approximately 200 million kilometers, the tidal force from the rogue planet on Earth is real, but not physically destructive to the planet itself. Earth holds together. But the orbital mechanics are another matter entirely. The gravitational perturbation that a Jupiter mass body at 1.3 astronomical units exerts on Earth is not a tidal deformation. It is an orbital perturbation, a change in Earth's velocity and direction of travel around the Sun, accumulated over the weeks during which the rogue planet is close enough to exert significant force. The magnitude of this perturbation depends sensitively on the geometry of the encounter, on whether Earth is on the same side of the Sun as the rogue planet during the closest approach, or on the opposite side, on the relative velocities, on the exact distance at closest approach. In the scenario we are following, perihelion at 1.3 astronomical units, Earth may or may not be on the same side of the Sun as the rogue planet at the critical moment. The geometry of the encounter is fixed by the trajectory. But the sensitivity to exact geometry is extreme, and small changes in the parameters produce dramatically different outcomes for Earth's orbit. In the scenario where Earth and the rogue planet are on the same side of the Sun during perihelion, the worst case for Earth, the gravitational perturbation is maximized. The rogue planet passes within approximately 50 million kilometers of Earth, about 1/3 of the Earth-Sun distance, at its closest approach to Earth specifically. This is not perihelion of the rogue planet's trajectory around the Sun. This is the closest approach between the rogue planet and Earth as a specific planet. 50 million kilometers. For comparison, Mars at its closest approach to Earth is about 55 million kilometers. The rogue planet, at its closest to Earth, is as close to us as Mars at opposition. But Mars has the mass of 0.107 Earth masses. This object has the mass of 318 Earths, or 1.1 Jupiters. Its gravitational force on Earth, at 50 million kilometers, is 318 times stronger than Mars at its closest, and Mars at its closest exerts essentially no measurable gravitational effect on Earth's orbit. The gravitational perturbation from the rogue planet at 50 million kilometers changes Earth's orbital velocity by a calculable amount. The exact number depends on the duration and geometry of the encounter, but estimates for a Jupiter mass flyby at this distance suggest changes in orbital velocity of the order of several kilometers per second accumulated over the encounter. Earth's orbital velocity is 30 kilometers per second. A change of even 1 kilometer per second, a 3% change, would alter Earth's orbit from its current nearly circular configuration to a noticeably elliptical one. The perihelion of the new orbit, Earth's closest approach to the Sun, might remain near its current value of approximately 1 AU. But the aphelion, Earth's furthest point from the Sun, might expand to 1.5 or 2 AU, carrying Earth out into the cold for half of each year. Or the orbit might be pushed inward, bringing Earth periodically closer to the Sun, raising temperatures during the new perihelion passage. Either outcome, more elliptical orbit, more eccentricity, has profound implications for Earth's climate. Earth's climate is stabilized in part by the low eccentricity of its current orbit. The variation in solar flux between perihelion and aphelion is only about 3%. Not enough to drive extreme seasonal differences beyond what axial tilt already produces. If the eccentricity increases to 0.2, the variation in solar flux becomes nearly 50%. The difference between the closest and furthest points from the Sun is half the total flux. Such a variation would drive seasonal temperature swings far beyond anything in the current climate record. Ice ages and warm periods, currently driven by the relatively subtle Milankovitch cycles, the long period changes in Earth's orbit and axial tilt that drive glacial interglacial cycles on timescales of 20,000 to 100,000 years, would be dwarfed. The annual variation in a high eccentricity orbit. Every year, Earth would swing from a hot near-Sun period to a cold far-Sun period. The climate system, calibrated over billions of years to a stable, nearly circular orbit, would face an entirely new regime. But orbital perturbation is not the only effect on Earth. The rogue planet's close passage also affects the Moon. The Moon is bound to Earth by gravity, following Earth in its orbit, held in its nearly circular lunar orbit by the mutual gravitational attraction between Earth and the Moon. The rogue planet's gravity acts on the Earth-Moon system as a whole, but it acts on Earth and the Moon separately, and because the Moon is in a different position than Earth's centre of mass during the encounter, the tidal force on the Earth-Moon system tries to stretch the system along the direction of the rogue planet. This is not a tidal force sufficient to disrupt the Moon. The Moon is far from any tidal disruption radius for a flyby at 50 million kilometers, but it is a perturbation sufficient to measurably change the Moon's orbit. The distance between Earth and Moon changes. The lunar orbital period, currently 27.3 days, may shift. The Moon's tidal influence on Earth, the tides, the stabilization of Earth's axial tilt, the gradual slowing of Earth's rotation, all of these depend on the Moon's orbital parameters, change the orbit, and all of these effects change with it. Earth's axial tilt, currently 23.5 degrees, responsible for the seasons, stabilized over millions of years by the gravitational influence of the Moon, is, on timescales of millions of years, potentially destabilizable by changes in the Moon's orbit. Mars has no large moon, and its axial tilt varies chaotically between 0 and 60 degrees over millions of years, driving extreme climate variation. Earth's tilt is stabilized by the Moon. If the Moon's orbit changes significantly, that stabilization changes. The long-term implications for Earth's climate on timescales of millions of years may be as significant as the immediate orbital perturbation. The rogue planet swings around the Sun. Perihelion passes. It recedes. The gravitational perturbation on Earth's orbit has been applied. The velocity change has been delivered over the weeks of close approach by the relentless pull of a world 318 times more massive than our own, passing through our neighborhood for the first and only time in history. The rogue planet exits the solar system on a hyperbolic trajectory, accelerated by the Sun's gravity, and then decelerated as it climbs back out of the gravitational well, ultimately escaping into interstellar space at a velocity close to its original 26 kilometers per second, plus or minus the energy it exchanged with the solar system during the encounter, i.e. BCE. By the laws of energy conservation, the energy the rogue planet took from or gave to the solar system's planets during the encounter is the energy that reshaped their orbits. Nothing is free. The rogue planet's exit trajectory was altered by the encounter too. It is now moving in a slightly different direction, slightly different speed. It continues into the galaxy, a wanderer, unchanged in its loneliness, carrying no record of what it passed through. The weeks around perihelion are the most intensely observed period in the history of science. Every instrument the civilization possesses is trained on the encounter. The gravitational dynamics are tracked in real time, the changing orbital velocities of all the inner planets, the perturbations rippling through the asteroid belt, the tidal distortions of the Sun's own shape as the massive intruder pulls on it. The Sun itself is measurably perturbed. A Jupiter-mass body at 1.3 astronomical units exerts a gravitational force on the Sun that is not trivial. The Sun wobbles very slightly around the common centre of mass between it and the rogue planet, as it wobbles today around the centre of mass between it and Jupiter. This wobble is small, the centre of mass of the Sun rogue planet system. At 1.3 AU is only a fraction of a solar radius above the Sun's surface, but it is real, and it means the Sun's gravitational influence on all the planets is very slightly shifted during the encounter. Every planet's orbit is being pulled not just by the rogue planet directly, but by the shifted position of the Sun's own gravitational centre. The Sun also responds thermally in a subtle way. The tidal force from the rogue planet at 1.3 astronomical units is not sufficient to deform the Sun significantly. The Sun is vastly more massive than the rogue planet. Note DHD. And its self-gravity completely dominates any tidal distortion from a Jupiter mass body at this distance. But the solar wind, the constant stream of charged particles flowing outward from the Sun's corona, is slightly deflected by the intense magnetic field of the passing rogue planet. If the rogue planet has retained a significant magnetic field from its formation, which is uncertain, since magnetic field generation requires a convecting liquid metal core, and after 2 billion years of cooling, the planet's interior may or may not maintain such a dynamo. Then, as the solar wind impinges on the rogue planet's magnetosphere, a complex interaction occurs. The rogue planet's magnetosphere, if present, deflects the solar wind, creating a bow shock on the sunward side and an extended magnetotail on the far side, exactly as Earth's magnetosphere does. During the closest approach, Earth and the inner planets are moving through a solar system in which the normal solar wind structure has been distorted by the rogue planet's magnetic presence, potentially affecting the geomagnetic environment of Earth and disrupting communication systems and power grids sensitive to geomagnetic variations. The visual spectacle from Earth's surface during perihelion is difficult to overstate. The rogue planet, at its closest approach to Earth, approximately 50 million kilometers, in the worst case scenario we have been following, is an object of unprecedented brilliance in the night sky. At this distance, reflecting whatever fraction of sunlight its dark, cold surface can manage, and self-emitting in the thermal infrared that is not visible to the human eye, it is nevertheless the brightest object in the night sky by an enormous margin. Its angular diameter at 50 million kilometers, given a physical diameter slightly larger than Jupiter's 140,000 kilometers, is approximately 0.19 degrees, roughly 1/3 the apparent diameter of the full moon. It is visibly a disk to the naked eye, not a star-like point, a disk. A world, visible without any instrument, its cloud bands perhaps just barely resolvable without optical aid, to those with the sharpest vision, a dark and enormous presence in the night sky that none of the traditions or mythologies or religions of the previous 10,000 years had anticipated, and that no prior generation of humans had ever seen. Body, the man says. The psychological impact of watching a Jupiter-sized world slowly brighten over years, then months, then weeks, until it is a visible disk in the sky. This is something that no analysis of gravitational mechanics can capture. Human beings are not orbital dynamics equations. They are storytelling animals, pattern recognition machines, creatures whose emotional responses to the environment are calibrated by hundreds of thousands of years of evolution to a world in which the sky was reliable, in which the stars were fixed, in which the planets moved but slowly and in predictable ways, in which the sun rose and set with metronomic regularity. The arrival of an object that violates all of this, that grows visibly brighter from night to night, that becomes a disk instead of a point, that is known precisely and scientifically to be changing the orbits of the planets. This is a civilizational trauma of a kind that has no historical precedent. Not everyone responds with reason. not everyone trusts the models. A civilization that has had 1,000 years to absorb the news still contains in its 21st century of warning individuals and communities and political movements that deny the reality of the threat, that assert the models are wrong, that claim the encounter will be harmless, that the scientists are fear-mongering, that the preparation programs are a waste of resources that could be spent on immediate needs. This is not a failing of human nature, it is human nature. It is the way that minds calibrated for immediate local threats respond to slow-moving, global, scientifically modelled ones. The history of climate change response in the 21st century is a template for what a 1,000-year warning period looks like in political terms. Urgent and insufficient, rational and irrational simultaneously, producing some preparation and not enough, driven by science that is precise and certain and largely unheeded in proportion to its precision and certainty. The perihelion passes, the rogue planet recedes. Within weeks, its apparent brightness begins to fade as the distance grows. Within months, it is no longer a disk to the naked eye. It has shrunk back to a point, but a point of extraordinary brightness, brighter than Venus has ever been in Earth's sky, clearly visible even in daylight when you know where to look. Within years, it fades to the brightness of a bright star. Within decades, it is barely visible to the naked eye. Within a century, it requires a telescope to find. The sky gradually returns to its familiar configuration, the stars in their constellations, the planets in their familiar motions, the moon cycling through its phases, except that the motions of the planets are not quite what they were. Earth's year is different, Mars's year is different, Venus moves differently. The sky is the same, and it is not the same, and only the most precise observation reveals the difference. But the difference is there, encoded in the orbital parameters of every inner planet, the permanent record of what passed through. The first year after perihelion is the year of assessment. The orbital parameters of all the planets are measured with exquisite precision. The new orbits are confirmed. Earth's eccentricity is increased, let us say from 0.17 to 0.14, an increase that is large by any measure, but not large enough to remove Earth from the habitable zone entirely. The new perihelion remains at approximately 0.9 astronomical units, marginally closer to the Sun than before. The new aphelion has expanded to approximately 1.23 astronomical units, further from the Sun than Mars's perihelion, in the region where liquid water becomes difficult to maintain at the surface without a significant greenhouse atmosphere. Earth will spend roughly half of each year closer to the Sun than now, and roughly half further from the Sun than now. The summer at perihelion will be hotter, the winter at aphelion will be colder. The amplitude of seasonal variation will be dramatically amplified beyond anything the current climate system was designed, by evolution, by the calibration of the entire biosphere, to handle. The climate response to the new orbital parameters begins immediately, because the climate system responds on timescales ranging from years to centuries, and on all of these timescales simultaneously. The first response is atmospheric. The changed solar flux at different parts of the orbit drives changes in atmospheric circulation patterns. The Hadley cells, the large-scale atmospheric circulation systems that govern the tropical climate and the distribution of precipitation, shift in response to the changed energy budget. The monsoon systems, which are driven by the seasonal differential heating of land and ocean, are disrupted. Regions that currently receive reliable seasonal rainfall begin to experience variable precipitation patterns. Agricultural systems, calibrated to the old seasonal pattern, are disrupted in the first decade. Food production in the most vulnerable regions, tropical and subtropical zones, where agriculture depends heavily on reliable monsoon rainfall, falls significantly below previous averages. This is not a famine in the acute sense of a complete crop failure, but it is a sustained depression in food production that, in the absence of technological compensation, would produce significant human suffering. The ocean responds more slowly. The ocean has an enormous thermal mass. It stores heat far more efficiently than the atmosphere or the land surface, and its circulation patterns, which currently distribute heat globally and moderate the climate at the regional level, take decades to centuries to fully adjust to new forcing. The oceanic thermohaline circulation, the global ocean conveyor belt that moves warm water from the tropics toward the poles, and cold and dense water from the poles toward the tropics, begins to shift as the temperature gradients that drive it change. The shift is slow, and its full consequences will not be apparent for centuries. But it is happening, and the civilization that survived the perihelion knows it is happening, and knows that the full climate adjustment will take centuries and will continue to change the habitability of different regions of Earth long after the rogue planet itself is invisible. The elevated impact rate from the perturbed asteroid belt and Kuiper belt is the most immediately dangerous legacy of the encounter for the civilization's infrastructure. In the decades before and after perihelion, the flux of large objects crossing Earth's orbit is elevated by an estimated factor of 10 to 50 over the background rate. This elevated flux will persist for centuries during which a civilization already under the stress of orbital change and climate disruption must also maintain a functioning planetary defense system capable of detecting, tracking, and deflecting or destroying objects that would otherwise cause regional or global catastrophe. This is technically achievable for a civilization with 1,000 years of preparation. It is not cheap. It is not easy. It is not something that can be done while simultaneously managing the agricultural disruption and the climate adjustment and the population relocations that the orbital change demands. It requires prioritization, coordination, and sustained effort across a period during which the civilization is already under extraordinary stress. The century after perihelion is the hardest, not the most dangerous in terms of acute physical threat. The perihelion itself was the peak of the gravitational perturbation, but the hardest in terms of the sustained civilizational effort required to navigate the consequences. The climate is changing in ways that are now precisely understood but not preventable. The orbital parameters are fixed. The elevation and impact risk is real and ongoing. The populations that need to be relocated from regions that are becoming uninhabitable are large. The agricultural systems that need to be rebuilt for the new climate regime require time and infrastructure that do not exist in sufficient quantity. The psychological burden of a civilization that has watched the sky change and knows the ground beneath it will change for centuries more is enormous. And through all of this, through the agricultural disruption and the climate shift and the impact defense and the population movement and the psychological burden, the long-term question hangs unanswered. The orbital dynamics question. The chaos question. The question of whether the perturbations delivered by the rogue planet will grow, driven by the gravitational interactions between the inner planets in their new orbital configuration, or will slowly damp out into a new stable arrangement. The simulations run after perihelion, with the measured post-encounter orbital parameters as inputs, show a range of outcomes. Some simulations produce stable inner solar systems for billions of years. Others produce growing instabilities that culminate in the loss of one or more inner planets over millions of years. Which outcome the real solar system follows cannot be determined from the immediate post-encounter measurements alone. The chaos is genuine, and the resolution of the chaos is genuinely uncertain. This uncertainty is in its way the deepest consequence of the encounter. The solar system before the rogue planet arrived was not guaranteed to be stable forever. Nothing in physics guarantees eternal stability to any finite system. But it was, by all evidence, stable on timescales of billions of years, with a low but non-zero probability of catastrophic instability on timescales of giga-years. After the encounter, the stability on long timescales is genuinely unknown in a way it was not unknown before. The probability of catastrophic instability has almost certainly increased. By how much? The simulations cannot say precisely, because the chaotic nature of the dynamics means that small uncertainties in the post-encounter orbital parameters produce large uncertainties in the long-term outcome. The civilization that survived the encounter will never know in its own lifetime which simulation is correct. It will monitor the planetary orbits with exquisite precision for centuries, watching for any sign of growing instability. It will run ever more sophisticated simulations as its computational technology improves, narrowing the uncertainty range as the precision of the orbital measurements improves. But the question of whether the solar system will remain stable for another billion years, or whether the chaos will cascade into catastrophe on a timescale of millions of years, is a question whose answer will not be delivered in any human lifetime. It is the question the universe asks and does not immediately answer. The civilization lives with the question, as it must, because there is no alternative. It is gone in astronomical terms within decades. At 26 kilometers per second, it covers one astronomical unit every 67 days. Within a year, it is beyond Mars's orbit. Within a decade, it is beyond Jupiter. Within a century, beyond the Kuiper Belt. Within a millennium, beyond the Oort cloud. It returns to the interstellar medium from which it came, resuming its slow orbit of the galaxy, its trajectory now slightly altered by the encounter with our Sun, its future calculated by no one. It will not pass through another stellar system for millions of years, perhaps hundreds of millions. It goes back into the dark, and the solar system it leaves behind is not the one it found. The immediate aftermath, the decades and centuries after perihelion, is where the long-term consequences crystallize. The inner planets have been perturbed, some significantly. Earth's orbit has changed. The question now is whether the new orbital configuration is stable, whether the perturbed orbits will remain perturbed but bounded, or whether the perturbations will grow, driven by gravitational interactions between the planets, producing further instability that cascades over millions of years into something catastrophic. This is where the mathematics of orbital mechanics becomes genuinely terrifying, because the solar system's orbital dynamics on long timescales are chaotic. Not disordered, chaotic in the precise mathematical sense, meaning that small differences in initial conditions produce exponentially diverging trajectories over time. The current solar system is already on the edge of this chaotic regime. Simulations of the solar system over the next 5 billion years show that there is approximately a 1% chance that Mercury's orbit will become sufficiently eccentric to either collide with Venus or be ejected from the solar system. And that in a small fraction of simulations, this leads to further causing the other inner planets. What would do? I said. What would be the same chaos for 50 years today? What would be the last 5 years we had in science? What would be the same chaos for science? What would be the same planet that would be? This 1% chance is driven by the existing, nearly imperceptible, chaotic dynamics of the solar system in its current, undisturbed configuration. Now, take that system and apply a gravitational kick that changes Earth's orbital eccentricity by a measurable amount. The chaotic dynamics of the perturbed system are different from those of the unperturbed system. The 1% chance of Mercury's catastrophic destabilization may become a 5% chance, or a 10% chance, or more. The long-term fate of the inner solar system, the orbital architecture that has been stable for 4.5 billion years, has been altered in a way that will play out over millions of years, in ways that no simulation run after the fact can predict with certainty, because the chaotic dynamics amplify any remaining uncertainty in the post-encounter orbital parameters exponentially with time. The inner solar system, after the rogue planet's passage, is a system that is stable in the short term. The planets are still there, the Sun is still there, Earth is still orbiting, but whose long-term stability is uncertain in a way it has never been before in the planet's history. Not certainly unstable, not certainly stable, chaotically uncertain. And that uncertainty will resolve over millions of years through the slow grinding of gravitational interactions into either a new, stable configuration or a catastrophic reorganization. Which outcome occurs is, in the strict mathematical sense, unknowable from the information available immediately after the encounter. The universe has rolled the dice. The result will take millions of years to read. In the meantime, the immediate effects on Earth's habitability are severe and specific. The changed orbit, let us say for the sake of concreteness, the Earth's new orbit has an eccentricity of 0.15, up from the current 0.17, means that Earth now passes significantly closer to the Sun at perihelion and significantly further at aphelion than it did before. The variation in solar flux over the course of the year has increased from 3% to roughly 30%. This is not a subtle change. This is the difference between different seasons and radically different climates in different parts of the year. The equatorial regions near perihelion experience temperatures significantly higher than anything in the current climate record. The poles near aphelion experience temperatures low enough to dramatically expand the polar ice caps. The atmospheric dynamics, the circulation patterns that currently distribute heat relatively evenly around the globe, driven by the mild seasonal variations of Earth's current orbit, are disrupted. New patterns emerge. Monsoon systems that are currently driven by the seasonal movement of the Sun change dramatically. Ocean circulation patterns, currently stabilized by the relatively mild temperature gradients of the current climate, shift. The biosphere does not go extinct. Life on Earth is extraordinarily resilient. It has survived the late heavy bombardment, the snowball Earth glaciations, 5 mass extinction events, and billions of years of slow stellar brightening that has gradually increased solar luminosity by approximately 30% since Earth's formation. The expanded seasonal variation of the new orbit is a challenge, but it is not a challenge that eliminates life. What it does is reshape the distribution of viable habitats on Earth's surface in ways that drive massive ecological disruption. The ecosystems that were adapted to the previous orbital configuration, to the previous range of seasonal variation, to the previous climate patterns, are maladapted to the new configuration. Species that cannot adapt quickly enough go extinct. Ecosystems that depended on stable climate patterns collapse and are replaced by others. The biosphere reorganizes, not over millions of years as in a normal evolutionary adaptation, but over centuries and millennia, at a pace that is fast by geological standards, but slow by human ones. A civilization living through this event, a civilization that detected the rogue planet 1,000 years in advance, that computed the encounter parameters with increasing precision as the object approached, that watched the trajectory calculations converge on a perihelion of 1.3 astronomical units, and understood what that meant, is a civilization that had time to prepare. Not time to prepare, there is no technology that could deflect a Jupiter-mass rogue planet. Not now, not in any foreseeable future. The gravitational interaction that would be required to change the trajectory of a 1.1 Jupiter-mass object by even a tiny fraction involves energies that dwarf anything a technological civilization is likely to be able to deploy. You cannot push a Jupiter-mass world out of the way. You cannot nudge it. You can observe it, model it, predict its effects, and prepare your civilization for those effects. That is all. And preparation over a millennium is not nothing. A civilization that knows its orbit is going to change can begin, centuries in advance, to adapt its agriculture, its cities, its infrastructure, its energy systems to the new orbital regime that will arrive after the encounter. It can develop underground habitats that are insensitive to surface temperature variation. It can develop food production systems that do not depend on stable seasonal patterns. It can relocate populations from regions that will become uninhabitable, very high latitude regions that will become too cold during the extended aphelion period, very low latitude regions that will become too hot during the new perihelion, to regions that will remain within habitable temperature ranges under the new climate. It can harden its technological infrastructure against the elevated impact risk from the perturbed asteroid belt. A civilization with 1,000 years of warning and the technological capacity to act on that warning can survive a rogue planet encounter with its civilization intact, even if the world it survives in is profoundly different from the one it inhabited before. But here is the thing that no amount of preparation can address, and that no technology in any foreseeable future can prevent: the long-term chaotic dynamics. The solar system after the encounter is not the solar system before it. The dice have been rolled. The outcome will take millions of years to reveal. A civilization that survives the encounter itself still lives in a solar system whose long-term orbital stability is compromised, whose future is uncertain in a way it was not uncertain before. Not certainly doomed, not certainly safe, uncertain. And uncertainty on geological timescales is a kind of vulnerability that no civilization has ever faced before, and that no technology can currently address. This is the true consequence of a rogue planet encounter. Not the immediate disruption, severe as that is. Not the climate change, dramatic as that will be. But the permanent alteration of the solar system's dynamical state, the rolling of a cosmic die, whose outcome will not be known for millions of years, and the knowledge, unavoidable, precise, scientifically certain, that the future is now less predictable than it was before. The rogue planet is gone. The solar system continues. Life continues. Civilization, if it was prepared and capable, continues. But the system is different now, in a way that is subtle to daily experience and enormous to geological time. The planets are still there, the sun still burns, Earth still orbits, but the orbit has changed. The stability has changed. The future has changed. And no one who watches the rogue planet recede into the dark, growing dimmer week by week as it climbs back out of the gravitational well, can be certain what that future holds, not over the centuries of a human civilization, but over the millions of years of a planet. There is, in this scenario, a profound and uncomfortable philosophical implication. We have spent the entire history of our civilization assuming that the solar system is fixed, that the planets move in their orbits as they always have, that Earth will continue to receive its current amount of sunlight in its current orbital pattern for the foreseeable future, that the background rate of asteroid impacts is roughly what it always has been, that the climate system operates within the range of its historical variation. These assumptions are not arbitrary. They are based on the observed stability of the solar system over 4.5 billion years, on the geological record that shows Earth's orbit has been nearly circular for at least hundreds of millions of years. The subject, and D, on the physics of orbital mechanics that confirms this stability. But rogue planets exist. They are common. The galaxy contains more of them than it contains stars. The solar system has been travelling through the galaxy for 4.5 billion years, and in that time, statistically, it has experienced numerous close encounters with passing stars, and probably with rogue planets as well. The current orbital configuration of the solar system is the result of 4.5 billion years of such encounters, most of them gentle, some of them not. The solar system we inhabit is not the primordial solar system. It is the solar system that survived. And the galaxy through which it is still travelling still contains trillions of dark, wandering worlds, each on its own trajectory, each indifferent to what it passes through, each a potential encounter if the geometry is right. The encounter we have described, a Jupiter-mass rogue planet at perihelion 1.3 astronomical units, is not the most extreme possible scenario. It is not the most common scenario. It is not the most common. It sits somewhere in the middle of the distribution of possible encounters, chosen for this thought experiment because it is dramatic enough to reveal the full range of effects while remaining physically realistic and scientifically grounded. More extreme scenarios, a closer perihelion, a larger mass, a direct trajectory through the inner solar system, produce correspondingly more extreme outcomes. Less extreme scenarios, a more distant perihelion, a lower mass, produce correspondingly milder ones. The space of possible rogue planet encounters spans from gravitationally interesting but essentially harmless to solar system destroying, and every point in between. What we cannot know, what no current technology can tell us, is whether any rogue planet currently in the interstellar median has a trajectory that will bring it into the solar system within the next 100,000 years. We cannot see them. They emit no detectable light at optical wavelengths. Their thermal infrared emission is extremely faint and requires specialized instruments to detect at even relatively close range. A Jupiter-mass rogue planet, 1 light-year away, closer than Proxima Centauri, on a trajectory that would bring it to perihelion within the inner solar system in 40,000 years, is currently undetectable by any instrument on Earth or in space. It could be there right now, dark and cold and approaching, and we would not know. This is not a claim that it is there. The probability that any specific rogue planet is on a trajectory that will bring it into the inner solar system is extraordinarily low. The solar system is a small target in the vast volume of the galaxy. The probability of a dangerous encounter within the next million years, based on the estimated population of rogue planets and the geometry of the galaxy, is estimated at roughly 1 in 100 million per year, low enough that it is essentially zero on any human timescale, but not zero over the full history of the solar system. The solar system has likely experienced multiple close encounters with rogue objects during its 4.5 billion year history, and the current orbital configuration of the planets is, in part, the record of those encounters. The stable remnant that survived them. What this scenario reveals, more than anything else, is the contingency of our existence. The fact that Earth orbits the Sun in a nearly circular orbit at 1 astronomical unit in a solar system whose giant planets shield it from most large impacts, with a large moon that stabilizes its axial tilt, with a magnetic field that protects it from solar wind, with an atmosphere that maintains a habitable temperature range. All of these conditions, which we take so completely for granted that they define our concept of normal, are contingent. All of these rocks, they are the product of a specific history, a specific sequence of events that started with the formation of the Sun and the planetary disk 4.5 billion years ago and has unfolded without any catastrophic disruption since. All of that, a different history, one that included a rogue planet encounter at the 1 perihelion distance at the 1 time in the solar system's evolution, and the conditions would be different. Earth might not be at 1 astronomical unit. Earth might not be there at all. The solar system is not eternal. It is not guaranteed. It is a temporary configuration of matter in a galaxy full of dark, wandering worlds, and its continued stability is contingent on the trajectories of objects it cannot see. Following paths set by gravitational dynamics that began billions of years ago in stellar nurseries that no longer exist, in encounters that no one witnessed. Moving through the dark at tens of kilometers per second toward destinations that the galaxy's dynamics will determine, indifferent to what lies in the way. Something is out there in the dark. Many somethings, in fact, trillions of them. Most will never come near us. The galaxy is too large, the targets too small, the trajectories too dispersed. But the universe is old, and the timescales are long. And in a galaxy with 1 trillion rogue planets moving through space for billions of years, some of those trajectories lead here. Some of them always have. The question is not whether the solar system has encountered them before. The question is whether the next one is aimed at us, and whether we will see it in time to do anything but watch. The answer, with our current technology, is no. We would not see it in time. We cannot see it at all. It moves through the galaxy in absolute darkness, producing no light, emitting no signal, following a trajectory set before the first human being looked up at the night sky and wondered what was out there. And whether it is aimed at us or not, whether the geometry of this particular dark wanderer's path brings it through our solar system or past it at a safe distance, or not at all, is a question that the universe has already answered and has not yet chosen to share. The dark is not empty. It is full of things we cannot see, and some of those things are moving